Hi, my name is Bosse Rüschmann, and this is the video presentation on my master's thesis, Reality-Proof Deep Learning for Bladder Cancer MRI, where I'm building a federated multitask 3D vision Mamba UNet. Bladder cancer is the 10th most common cancer in the world, with approximately 570,000 new cases and over 200,000 deaths in 2020 alone. And that incidence is projected to double in the next 15 years. And if bladder cancer metastasizes, so when it goes into the muscle, then the survival rate drops dramatically. That's why finding out whether the bladder cancer actually invades the muscle, meaning the bladder wall, is the key distinction. This is called staging. The muscle invasion determines the survival prospects and also the treatment options. Non-muscle invasive cancer is usually treated endoscopically, where the cancer is essentially cut out. And for that, it's essential to have an accurate outline or segmentation of the cancer to know where to cut, because you don't want to cut too much, but if you miss some of the cancer, then it might recur or even metastasize. Muscle invasive cancer, on the other hand, is treated by either fully removing the bladder and or chemotherapy. Accurate staging is so important because if you miss that the cancer invaded the muscle, the patient may die. And vice versa, you don't want to remove the full bladder if it actually wasn't invasive. And staging the cancer correctly from MRI images, again, depends on accurate segmentation of the cancer and of the bladder wall, because you want to see where they overlap. But bladder cancer treatment is currently very error-prone. The normal invasive way of staging cancer is by cystoscopy, but that's also very error-prone. That's why we're trying to see if it can be more accurately done by MRIs. An older study with MP MRIs showed that almost half of all cancers were misstaged, and newer studies show around 15% misstaging, so still a huge problem. And it's similar for removing non-muscle invasive cancer. The current surgeries are so inaccurate that when a study took a second look, there was still tumor left in almost a third of cases. And it's so inaccurate that non-muscle invasive bladder cancer recurs in up to 78% of cases. So what we need is really accurate bladder cancer segmentation and staging. And this is where deep learning from MRIs may come in. But the big problem with current AI for bladder cancer is that it often doesn't work in the real world. It's not reality proof. In machine learning terms, the current models lack generalizability. They are often trained on a single or two hospitals' data and don't work on other hospitals with different MRI devices. So the models often show fantastic results on paper, often a DICE score of 95%, but they are not deployable in the real-world multi-institutional settings. And studies that try their models on different hospitals' data actually only achieve DICE scores of 80%, and 80% is just not good enough in this high-stakes situation. And this problem is only made worse by data barriers and privacy concerns, because you can't just pool everyone's data and build a model that works for all. And you can't train a model for each hospital because they actually don't have expensively labeled data themselves. So, what's the solution? Kao AI tried to tackle exactly these problems. So they created a new bladder cancer MRI dataset with pixel-wise tumor annotations and corresponding muscle invasion labels. MRI scans from 275 participants from 4 different hospitals. The data was published in October 2024 and has so far remained quite unexplored, and my thesis will be based on this data. The dataset is perfect for research on making models more generalizable to different hospitals, especially new hospitals with very few data. And the dataset is perfect for research on federated learning. Federated learning is a way to train AI models decentrally across multiple hospitals without sharing any patient data. So instead of sending data to a central server, each site trains their own models locally, and then they only share the model updates. And then a central server combines the model updates into one global model that it then gives back to the different hospitals. And beyond the obvious privacy advantage, this also improves model generalization. And federated models perform nearly as good on paper as centrally trained ones. So Kao AI already trained and tested baseline models on their data using a centralized and federated learning for both bladder cancer segmentation and staging classification. Their results, though, are not yet good enough for clinical usage. They have DICE scores of around 0.84. But they actually show only a very small difference between the federated and decentralized learning, and this suggests that the federated learning approach is working well, and the problem may lie with their modeling approach. First, they did not use the newest model architectures, and second, they train on 2D pixel patches, so their model doesn't take the 3D volume of the actually three-dimensional MRI scans into account. And third, they train two separate models for segmentation and staging, which also doesn't make sense because the two tasks are so related you would want the tasks to inform each other. So, I want to build on the federated learning work by Kao AI, but I will use a frontier model architecture with 3D processing and multitask segmentation and staging at the same time. So we first have to decide on the best model architecture for 3D context. The multitask is mainly a question of the numbers of neurons. But the current models, they struggle with 3D long-range data. That's because in the three-dimensional MRI scans, features like a tumor edge, they can be far apart across slides. CNNs and UNets, they are limited in their long-range modeling capabilities because a convolution only looks at a small neighborhood of pixels, and so to connect distant parts, you really need many layers or a big kernel. Transformers are good at capturing long-range relationships because they look at every token alongside every other token parallel at the same time to compute attention. But as the length increases, the computational complexity increases exponentially. So on our very long three-dimensional MRI scan data, the computational complexity for transformers would explode. And hybrid CNN transformer methods, they either have local kernels or the quadratic cost. So we need a 3D method that sees long range and scales linearly. One solution may be state space models, or SSMs. This is a new class of model that is emerging as an alternative to transformer-based models in all kinds of domains and also medical imaging. SSMs turn the data into a sequence, and they keep track of hidden variables, the state of a system. They describe the system dynamics through a series of first-order differential equations. And very importantly, they do one update at a time, per time step, so pixel or voxel position, instead of comparing all positions. And that allows them to model long-range dependencies with linear computational complexity. And so SSM excel at long-range interactions. 3D is possible. They have faster training and inference, and they actually match the vision transformer accuracy at only half the compute. There are many variations of state space models, and the one that I'm going to use was developed specifically for medical imaging and is called the Vision Mamba UNet. How this architecture works in detail is beyond the scope of this video. In short, the model replaces the encoder of a standard UNet with Vision Mamba VSS blocks, which bring state space modeling capabilities into a convolutional framework. The architecture has an asymmetrical encoder-decoder structure with very few convolutional layers. But this model so far has only been developed for 2D processing. And that brings us to the thesis plan. This thesis is structured in 4 phases, and for each step I will measure the improvements. First, I will reproduce the Kao AI 2D UNet and ResNet baselines, both centrally and in a federated setup. This is easy as their code is public. Second, I will swap their segmentation UNet backbone with the 2-dimensional Vision Mamba model from the original Vision Mamba paper that has also published the code. Third, I will integrate staging into the Vision Mamba to create and train a multitask model that can do segmentation and staging at once. And this step I hypothesize will bring the biggest performance gains. Fourth, I will expand the multitask Vision Mamba model to 3D, so from 2D pixel patches to 3D voxel patches. The first 2 steps are relatively low risk as public code is available, so there are my minimal viable analysis. And steps 3 and 4 require significant engineering and are where most of the innovation lies. So the research question guiding this thesis is, can a federated multitask 3D Vision Mamba UNet outperform separate 2D baselines in segmentation and staging on the Kao AI multi-centered dataset? If successful, this thesis would be quite novel. It would be the first application of a pure three-dimensional vision Mamba UNet for bladder cancer, and indeed the first state space model for bladder cancer in general. It would also be the first vision Mamba model with federated learning and multitask, and the first reproduction and improvement on the KO-AI dataset. This thesis would contribute to making AI for bladder cancer segmentation and staging more generalizable, deployable, and privacy compliant. In short, reality-proof. It will hopefully improve bladder tumor segmentation and staging predictions to support treatment planning, ideally DICE and AUC over 0.9. It will improve deployability across hospitals without central data sharing, and it will enable faster inference with reduced compute requirements. Ultimately, this could lead to higher adoption across hospitals and thus better clinical outcomes. So that's it. Thank you very much for watching.